People are here. So just to let you know, this is all recorded. We have to inform you that that's the case for GDPR reasons.
Can we start?
Yeah, let's give it a go.
Okay. On behalf of European Account Association, I would like to welcome everybody to this Python course for accounting research. I also would like to thank Professor Martin for offering this course. This is the second session out of the 5 that the European Account Association is offering to our members. This session will be recorded and will be available to all participants. And in case you don't want your voice to be recorded, please turn off your camera and mic. In case you have any question during this session, please open your mic or write in the chat window. Mart, you can start now your second session. Thank you.
Okay, guys, so welcome. Today we're going to again sort of dig a bit deeper into Python and what you can do with it. What I'm going to do, this is a twofold or two-part session. And I'm not going to take you through all the lines of programming. I think last week I showed you how to get through stuff and get stuff done with a very simple data set from the Google mobility data. This time the data is a bit more complex, but I also want to sort of spend some time on debriefing the first assignment. So I'll suggest to start first with the main course, and that has to do with exploring, managing, and cleaning and data for US bank holding companies. So that should be now on your view. Is the view? Can you all see the screen well?
Yes.
Yeah. Okay. So that's good. Are there any questions? And so please chip in if you have questions. Anything that I can help you with, make this all understandable. I mean, I'm here for you, and you have now an hour time to ask me everything that you want to know. So feel free to ask questions. If not, I'll just give it a go. So one of the things that we'll have to do or understand learning the data from Python or using Python and Pandas in particular is to munch data, and that is, dealing with missing observations, cleaning data, think about column names and so forth. And so instead of using the easy, convenient data that I used last week from Google, in this case, I'm going to focus on, what is it? Yeah, US bank holding company data, right? I'm just, let me go, sorry. I'm going to use the European Banking Authority data from the risk dashboard. Yes, sorry, just got sidetracked by the screen that I had in view. So this is the next step, and so what we'll do is, a step further into to dealing with the data using Pandas, and so we'll focus the attention to what it calls index, split, apply, and combine. So there's, I think, where the power of Pandas is, because unlike Stata or say SPSS, I think Pandas allows you to have multiple data frames in memory, and that makes combining data and splitting data and stuff much easier, and also cleaning up data and all sorts of operations that you can perform on data is easier using Pandas, and that is what I'm going to use. So instead of using the easy data that we had from last week from Google, we're now going to take some more complex data, and the reason that I'm using that more complex data is, or one of the reasons that I do that is, quite often you'll find some report where they have data, you can download the data, but then the downloaded data looks kind of messy and awful. And an example of that is the European Banking Authority risk dashboard. There's a treasure trove of data in there. And this is, if you go to the European Banking Authority website, this is the main website, and you click on the risk dashboard. And what you see is a PDF, but the PDF is kind of weird in that, it's only Excel tables and graphs. So graphs, and then tables below, and so on and on and on and on. You know, it's a large package with mainly screen prints of financial data from banks in Europe, and these are risk indicators. And what you can see here is clearly that it's all, you know, the source of this data is obviously something like Excel. The bad thing is that, you know, there's very few programs that can sort of cope with this PDF data. And so luckily the European Banking Authority, they have what they call the interactive tool, which then makes the same data available in Excel. And so here's that interactive tool. Now there's some sort of things where you can click on, and there's some sheets here. And all the data here in these sheets is can be used for data analysis. So in particular, you know, the sheet's called data, and I think there's also data annex. There's where all the data is stored, which is kind of cool. The thing is, what we will do now is, you know, look at that, you know, see if we can load the data into Python, Pandas, and then make sensible data out of that and present some, you know, some statistics on that as well. So what you need to do is download that spreadsheet called Interactive Dashboard. That's this one. Save it to a drive, and then open it up in Excel using the Pandas read Excel command. Now you can find the columns for Excel for the Excel sheet here. So you have to inform Pandas, like, you know, you have to search for columns A, F, and BI to get that data. So that's more or less somewhere. That's this blue part here, which starts AF and then goes on to BI. And then you have to tell it to skip the first row, because the first row, that's this one here, is empty. And you have to tell it to look at sheet name called data, and that's this one here. Once you get that command running, if you run that, you get this output here. So what you see here is a data frame, but you will notice a couple of things, and I pointed it out in the observations, is that you can see that there's funny stuff going on here. So one column name has a dot in it, and that's not because of the EBA, but there must be a duplicate column also with the same name, something like that. So some of these column names have a dot, like here, and some of them may have not that, but you want to get rid of that one because it's kind of not very smart to use that. Some of the cells here, they have dots. That should be a missing observation, or nans. The column name is weird in that it has a strange structure in that the first letters here are the country code, and then the variable name is a codified variable name. And so we have to break that name part into two parts to make it a country code and a variable, a column for the variable name and a country variable name. So we have to split that column into two parts. There are some observations that start with EU. So these are the average for the European Union, but that's not really the country. So we should get rid of that as well. And then the variable codes here, like SVC 29, SVC 13, nobody understands that. And so we have to make that more easy to understand, which we can do with a dictionary. And then to finalize this, ideally, we want the data frame to feature the variable names in columns. So the variable names should all have a column, which is currently not the case because all the columns are years. So what we have to do is use pivot to move these year indicators or quarter indicators to the index at the left, and then the country as well. And then the column names, that should be these variable names, SVC 13, these should be the variable names. And then you have a data frame that is useful for research. Now, most of the things are, the solutions or the preparation file is available on GitHub. And so you can sort of go through that file yourself. And so I'll take you quickly through the most, the trivial things, and I'll spend some time on things that are probably more tricky to understand. So, so what we have here, the Pandas data frame here is a copy of this file or this spreadsheet part here. And as you can see here, there's where EU start, and there's where, you know, this cell is EU with variable names, then Austria, Belgium, etc. until SK, what is that? This is Slovenia, I think. And so you have all these countries there. And what you see in this spreadsheet is the same data as is now available for us in Pandas. As I said, there's a lot of stuff we have to clean up to make it a workable data frame. So one thing you can do is that, given that all the information here, all the numbers here are just numbers, there's no text in these cells. So the only odd one out column here is column AF, which has the name and the country and the variable name as well. And so what we can do is hide that column and turn it into an index. Yeah. So that can be done by this command, you know, set index name. And then the advantage of that is that the name column, this one here, will be protected from any operations we perform on the columns here and on the variable or on the cells. So quite often I use an index to protect a column from being changed or modified. And so that's one of the tricks of the index. One of the most powerful things in Pandas is the index. And one of the reasons I use it is to hide columns there. Okay, so the first thing we can do is rename the column names. If you just use list comprehension to go through these column names, you can do that by running this command, X for X in the data frame. So it presents all the column names here. And so these are these column names of the data sheet, but somehow at the opening of that file, there were duplicate entries of the 2014 September data. And so they give it a .1. And at the end of the year, there's also a column, at the end of the period, you see there's September 2021, and there's a dot as well. So we have to get rid of that. And the way to do that is to get rid of that is to use list comprehension, and then this part where you go through all these, you loop through all the column names. Watch the way it's done here. But then you perform an operation. What you want is if it is a string, if it's a number like here, then you should keep it as a number. And if it's not a number, then you have to split that column name. So in this case here, it's seen as a text field, and then you split it into parts, and then this part extracts the first part from the column name and then gets rid of the .1, and that is what you want. So this line here takes the first item from the split string, which is the 2014-09 part, and then gets rid of the .1. And so then you have a clean list of column names. That's the one here. Now you can apply that to all the columns by using the data frame column method here. And so you say for the data frame columns, I want them to be the columns like shown here. And if you perform that operation, you get very neat column names. Now, none of these columns are weird. They all have a nice format like 2014-09 to 12, and the dots have gone. Yeah, so that's one way of cleaning, using list comprehension to clean all the column names. Done that. So if you go through the cell to the data frame, you see that there's funny cells here. They have a dot. They represent missing observation, and the European Banking Authority, they sort of code that as a dot, or that may be the software that they use that codes it as a dot. We should get rid of these dots. One way of doing that is very powerful, and that is this method here. And remember that one. This is a very powerful trick to get rid of all non-numbers in your data frame. So what you do here is I apply to the data frame, I force all the cells to be numbers. And then if there's some form of protest, I tell Pandas to do that regardless. And so to coerce, literally coerce all the non-numerical information in the data frame, so the dots, but maybe text items or data items, everything will be forced into numbers. The result is that all the non-numerical information will be transformed in missing information called nans, and these are perfectly readable and understandable and easy to manipulate using your statistical software or Pandas itself. So you will use this trick very often when you clean up data, because the trick is for the entire data frame, you force out all the non-numbers and keep in all the numbers as is. Yeah. So if I run that trick, you can sort of check the type of the column names or the columns, and you see that they're all floats now. Whereas before, all these columns were seen as objects, and objects can be text or a combination of text and numbers. But if your column has object data in it, it's not really clean. And by performing this coerce, apply to numeric coerce trick, in one fell swoop, you turn all the information into numerical data, which is now floats. And here you have it. Here's the result. So you can take from the first 8 rows, you take the last 4. That's a trick to show some of these nans. And you can see that where there were dots in the past, they have now all become missing numbers. And Pandas is very well equipped to deal with missing numbers.
Martin?
Yeah.
Do you think it's a good thing to check all the column types before you do anything? Because you said there one was object. I don't know about the others. So is it a good thing to check all the columns before you go on?
Yeah, quite. What you can do quite often is to use, if you download the data, I'm not sure if I can do it here, but what it can do, let me see. I'm just adding. So what you can do is df info. And so this is a different data frame because this is one. But what you do is if you type in df info, that one here, from the data frame that is in memory as df, you get a specification of the types of data there. So if you're not familiar with the data, it's always handy to do df info or dtypes. And then you get basically objects integrated. So in this data frame, that one here, baz is clearly numerical. So you can see that baz here is an integer. Yeah. So either you do df info or you do dtypes, and then you get the right, you get information about the source of the data. In many cases, you don't have to worry about it. And sometimes the data is very straightforward. But if you run into trouble, then you might as well do dtypes to check out why things are not really working as you expected it to be.
So I see that you're taking a lot of time during the cleaning, because that's something very important, but that you're going to do just once, and the next time you don't have to do it anymore. So because since the data comes from Excel, you could do some work there, but once you do the programming, so you're gonna have to do just once, right?
That's the idea, yeah. So the thing with this risk dashboard is that it is every time it will be updated. And so I often use this analysis because you can find some treasure troves in the data. But every time I download the data from the European Banking Authority, I run the program, and then I have basically the data the way I want it to be, without having to think a lot about, once the program works, and I can show you down below, how that works. Once it works, you can sort of apply it to updates, and then you get your updated data in a very nice and clean shape. That's the whole idea of using Python. Once you put this all into a program, then you don't have to ever worry about it again. Yeah, only for making some updates with variable names, maybe, or sometime. Yeah.
Thank you.
The next time is one of the things that that is kind of a tricky trick is to, once we have this data frame here, which now has proper data and so forth, what we're going to do here is split the column into 2 parts. We separate out the country part, EU or SK, from the variable part. And we can do that using the split method here from Python. So suppose I have a string called EU dash or underscore lic underscore 70. I can split it on the basis of the underscore, the first one, and then you get basically a list of 2 items. So I'm going to split this string S into 2 parts, and the result will be a list with 2 items, the country name and the variable column. So this is, this logic can be applied to that column. And the trick to do that, it looks like a long line, and I put the documentation here in the link, that's Stack Overflow. And what you can do here is to apply that string splitting trick to the column, the data frame column called name. So that the name column of the data frame. Now, currently the name is an index, and so you have to reset the index. That's what you do here, and then you split it up into 2 parts using this command here. You apply the string split method here, as shown in the cell above, and then you rename the parts from that split into a country part and a variable part, and then you have, if you do that, you will see that the data frame now has a name column, a country column, and a variable column. And if you show that, using head2, you get basically the information. First the name as it was, then the country as we wanted, and the variable as well. So once we have broken up that name column into 2 parts, we don't need the name column any longer because its role has now been replaced by the country variable and the country and variable column names. And so we use the drop command to do that. Now I'm going to skip through the EU part, how to eliminate that, because that was more or less taught in the last week, how to select separate rows. And even if you leave EU in, there's no harm done. The other thing here is we don't know exactly what these variable names mean, but we can find in the Excel spreadsheet from the European Banking Authority, there is a sheet with the relevant data. Yeah, here we have it. Is that it? RI database? Yeah. So we can load that. We can sort of open that Excel file, load the RI database, which is this tab here, and then we can collect the information from, I think, this part, DNE. Yeah, DNE. You can collect the information from columns DNE here, and then put it into a data frame using this function here. So again, here, I wrote a function for that. The only thing that I now can do, I can use this multiple times, but also if I have an updated version of the spreadsheet, I can sort of change the file name variable, which I defined at the top of this file, and then reread an updated file. The result will be this dictionary here, or a data frame with all the the codes for the variables, like SVC3 is Common Equity Tier 1 ratio, leverage ratio, etc., etc. So we can run a check. Once we have this data field with the RI definitions, we can locate number. We can locate the index with the name SVC13, and that's the leverage ratio. So that shows up here. Okay, so now we have we now have everything set up for proper, proper analysis. The data stream is now in a good shape, not perfect yet, but we can sort of change the shape and then sort of start doing analysis on that. So reshaping the data. The first thing you should do often is to melt it. And the melting comes, this melt term is from R. R uses the same thing. It has to do with somebody who has a steel bar and then melts it into fluid steel. So that it becomes like from a block or a square, it becomes like a thread, of hot steel melting out. And so there, that turns something like a squared data frame into a very thin one, and that's the melt process. So we're going to melt this data frame that we now have, this one here, we're going to melt it and then turn it into a single column with sufficient indexes to make it work for us. So the melting part is quite handy, and some other, many databases use this approach, and so therefore handy to know. So yeah, so in its current form, I think you can work with the data. So you can find, for example, the liquidity coverage ratio for Austria, but then you have to use a tuple, which nobody likes. And then if you do some effort, you can get this graph by plotting that data. But it's much easier to use the melt command and then melt that data frame into a single column. And so I'm looking at this data frame that we have, and that is this one here. We're going to melt it, and what we want is we want the country and the current column names as an index, and we want the variable names as the column names. So the variable names should be the column. Yeah, oh yeah, that says value variables. The value variables should be the current, which is the list of the names of the columns currently. That should be the value variables of the data frame. So that's basically these ones. These should be the variable vars. ID vars should be variable and country. And then the value name should be value. Well, sometimes you have to play with these names to get it right. If you do it right, you you execute the melt command. And then after that, you have a data frame without an index. So we have to inform Pandas basically to apply an index to the melted data frame called DFM, the M for melt. And then we have this one as a result, this data frame as a result. Now, what you can see, there's about 20,000 rows here, and there's only one column, and the column is a value column. And all the other, the indices will tell us what variable we have, which country it is from, and which date it has. So this is extremely handy data for all sorts of operations. So this is easier to deal with. But for inspection of variables, it's not very handy, because if we want to, compare columns next to each other, then this is pretty bad. Yeah, so we're not there yet, but we're almost there. We now have a melted column, and that's often the starting point for further reshaping. But before that, I'm going to sort of bring this all together in a function. That was, I think, Dutra's comment here. Is all the lines above that create that data frame can be executed in a definition here, and I call it the risk indicators read function, read risk indicators. The only inputs it needs is a file name and a sheet name, and then it gets all the data from for the data frame that I just showed. So I can run this one here, and then the result is there's 3 results from the data frame. So that's the great thing about these functions. They can give us back multiple results. So first, there's the data frame, more or less a copy of the one here shown by the European Banking Authority. So that's what I call DF, then the melted version. And then I have a list of European countries, more or less to see which countries participate in the data. And so these are the outputs from this function. And I have to only run it once. And then this function gets me all the data and turns it into 3 items, 2 data frames, and a list that I can use for research. Yeah. So again, here, printing the countries. This is the data frame, and this is the melted data frame. And the melted data frame can now be used for various analyses, quite handy. Yeah. So suppose I want common equity T1 capital ratio, which is SVC3. If I want that for, if I want that variable, common equity T1, for group by date. So I want to, find the average of the Common Equity Tier 1 ratio, which is the bank capital ratio that investors are interested in. If I want the means of that for any given date, I can use this command here. I can locate the variable, and I can also group them by year, by date, and then look at the means. Now, if I want to plot that, I do it using the bar plot, and then you get all the information we need. And what we see that over the since 2014, so since the single supervisory mechanism came into in effect, we see that bank capital has increased until the end of 2021. What is that? I just can't get the last. Oh yeah, here. You can see at the very end, there's a bit of dipping of capital rates. So that's probably the effect of the COVID crisis still affecting some of the banks in Europe. So capitalization have gone low, but they have steadily increased over the last year. So there's clearly a trend in the capital ratios, an upward trend, which are the means. How does it work for the medians? Yeah, there's a bit. It's more choppy if you use the medians. So let's stick to the means. So here we group by date. But we can also, given that the data frame can be grouped on multiple dimensions, country and date at least, you can sort of group by country in this case, and then see which countries have the highest capitalized banks. Now, no surprise that the Nordics and the banks, around the Baltics are highly capitalized. So poorly capitalized is Spain, and Italy still, and what is it? And Portugal, although all these, they're kind of okay. Austria still has a couple of weaker capitalized banks. So this gives you, this gives a fairly good information about the average numbers. The average capitalization of countries in Europe. So, and the data informs us basically that confirms our priors. The Nordic countries have high capital, and the countries around the Mediterranean or south of Europe, they have slightly weaker capital. Although I must say this is the average over all the years from 2014, and so as things have improved, we can see that there's improvement, and some of the southern countries may have improved stronger than some of the northern countries. You never know. So that's one. So MELT is important for getting a workable data frame. But sometimes we want a more traditional approach where you have the country and the date in one column in the index, and then the column names are the subsequent variables. That very much looks like a data set from Stata and maybe other statistical packages. So in order to do that, we can use pivoting. And the pivot function from Pandas is very much the same, very similar to that one of Excel. Yeah, so so what it does is just a copy of the Excel pivot approach. If you follow the instructions from Pandas itself, you get this example here. So here you have a data set called DF, which is organized like this with three variables. And we want to pivot it in such a way that the columns, the bar column here, that will be the column names. So columns will be extracted from bar. The values are bars. So these are the numerical values, bars. Not sure what we do with zoo. And foo is going to be the index. Yeah. So if I run pivot, you can sort of pivot that, reshape that data frame in one go, and then you have a pivoted database. Problem arise here is that the pivot works nice if you have a single index, but if you look at the DFM, the melted frame, we have three variables: variable, country, and date. And the resulting data frame should have two, namely country and date. Country and date, yes. So you should have a multi-index. There's a multi-index frame going in, and you should have a multi-index coming back. Now, that doesn't work with pivot per se, Oh, but you can use pivot table, which is a helper function, and pivot table can do the trick for us. So that allows you to pivot it in a very straightforward way. We want the values. There should be the value column from DFM. That's this column here. The value column. And then the index should be country and date. And the columns, they should be from variable. And variable is this. That's the leftmost column here, SVZ 12, AQT 3.1, whatever that means. So if we feed that into the pivot table command, you get this table as a result. So DFP is pivot, is the result of the pivot command here. And then now we have a properly formatted data frame with country and date neatly in the index, and then all your variable names are in the columns. Nice and compact, 837 rows times 22 columns. So it's a nice data frame. Okay, if you're lazy like me, then I often rely on commands like stack and unstack. They do the same thing, but melt is to be preferred, because if you use stack, so if you stack a data frame, often stack returns a column name called 0, which you then have to rename, which is kind of not so great. So use melt whenever you can, even though it can take some time to figure out the right way of doing that. So far, this is basically the approach to take whenever you have this complex European data from the European Banking Authority, the messy data that I just showed from these columns. This one, the mess here, so the relative mess, is now converted into a very neat data frame called DFP, where we have countries here, variables in the index, and then column names as we go. With that data, we can now easily do, say, grouping operations. So the grouping stuff will be discussed on Thursday. So I'll just show you a couple of things you can do. You can select, for example, non-performing loans and advances by country and by date. And by date, you do it. Sorry, got there. You can group by country, more or less the way we did, but we then select just a column. We don't have to use lock or something like that. So non-performing loans, group by country, and it shows the means here. This for dates, group by date, so you can look at the evolution of non-performing loans over time, and we can plot that. So what we have here is from the data frame, we select column AQT3, which is non-performing loans. We group them by date, because the date is in the index. We take the mean, and then we plot that. And what you can see is non-performing loans in Europe have gone down. But there's a slight uptick here, I think. Why is that? It's still going down all the time. So that's kind of good. So despite all these complaints about Italian banks suffering from the forense and whatever, or forense, all these non-performing loans, there's a steadily downrift there going on. Now, there's also the stuff you can do with group by, and I'll come back to that on Thursday. One thing, if you group, so you can see here, I select a variable here and then use group by. That's fine, but sometimes you want to refer more often to group by, say, data that is grouped by date. Now, to make that your life easier, Pandas has a facility called the group by object. And so what you can do is make an object of the group data. So in this case, I'm using the panel data, DFP. That's this data frame here. I can turn that, make a group object, which is called DFP group by country. And then the entire panel frame structure is then grouped by country for and put in a separate data frame called, or a separate object called df group here, dfp gp for group. And so very easy then is for that group, I can, suppose I want to know all the minimum values for each country. I can just call that group object and call for its minimum values. And then for all the variables and all the countries, I get the minimum values. Yeah, I can also do max, and then I got all the max values here. So it's very powerful if you if you want one statistic for all countries and all neatly grouped by country. You create an object called DFG group, and you perform operations on that group. Yeah, in this case also, suppose I want I think non-performing loans from the group, and I can ask for the statistics first and last. So what is the non-performing loans at the start of the sample period, and what is this non-performing loans at the end of the period, and I can plot them using this command here. And then you can see that in particular, Cyprus has improved a lot. They had lots of non-performing loans at start 2014, and it's gone down. Same is true for Greece and for Ireland. Yeah, so this shows you in one line the evolution of non-performing loans for each European country. Now the stuff on cumulative stuff, I'll come back on it on Thursday. So, but you can still use the same group to do all sorts of other tricks. The last thing for this part here is the group by and transform tool or trick. Is sometimes you want a column in your data frame to represent the group average for some sort of group, and apply that for all cells in that group without really making a separate data frame. You can sort of create an additional column in your data frame that contains the average for a group, or the mean or the median for some sort of group. If you want to add such a column with, say for if you want to demean or normalize data, you can use the transform trick here. Yeah, so what I'm going to do here is more or less create a data frame or a set of columns that has the same structure as the original data frame, DFP, but where all the values are the averages, the country averages for, say, one variable, say non-performing loans. So if I use the transform trick here, we just create a column or a data frame of the same structure as the original data frame, DFP, and that can be used, for example, to take the difference between your current observation and the average for some country going forward. So transform is when you need an additional column in your data set that represents some statistics that can be applied to all rows of your data frame. One way of doing that is for a single variable. I can transform all these values into the average non-performing loans value for all countries, and then you do that by this command here. Yeah. Alternatively, you can create a sort of a copied data frame which has all these transformed values in it. So I can create an additional data frame which looks like the original DFP panel data frame, but then only presents the country averages for each of the countries participating, and that's by using the transform trick here. Yeah. So if I do that using transform and taking the means per country, what you can see is that all these countries, for each variable, you have the same, country averages reflected in a column. So you can see there's a lot of repetition here, but sometimes you need these averages to compare it to, say, the annual value for Austria for 2013, and take that, compare that to the mean for that country, the overall mean for that country in the sample. So that is how to create, a copy with the same structure as the original, but where you have grouped the data and then applied some operation to the group data, in this case, transformed it to the mean. So this, DF means data frame has the same dimensions as as the original data frame called DFP. So if I do that, I can show DFP. So these are the original values from DFP. And these, the values here are the means for that country. So that's basically, this part of the session for shaping and what was the idea today of to do index, split, apply, and combine. So this, gives you an idea about how to sort of do munging, in particular when it comes to splitting, transforming, combining, etc. So any questions so far? Don't worry, you can do the test. So we have about, I sent in an assignment a bit earlier. That's the assignment here. Oh yeah, the assignment was using information from bank holding companies, and what I wanted you to do is to sort of, get that data into shape. And munch that data. What was the plan? There's a lot of stuff going on here. Okay, so yeah. So a couple of things that I, that may, in this assignment that may have had your attention. The data from the Federal Reserve Bank is free, but it has very similar structure to that of Compustat and Compustat data. So it's quarterly data, which is available in Compustat as well. And there's accounting data, there's an identifier called RSS9001, and there's a date variable called RSSD 4x9. So the data from the bank holding company is free, but it's very similar to that of Compustat. So what you see here, you can apply to Compustat data as well. One thing that I find kind of powerful with this data set is that if you want to load that data, it's all stored in zip files on my drive, and so I can use this glob command from, and whoever invented that for Python deserves a prize, because what it does is it goes through your folder, looks at all the files that start with bhcf, end with zip, and then loads them into memory. And then, this function then concatenates all these rows in one fell swoop into a single data frame. So just one command, and you load about, 12 data sets. They're all zipped, but it unzips it for you, and everything's automated. And the result is now that you have a database with about 24,000 rows and 2,300 columns, which is far too big. So, but it's all done in a very simple way, like one function, and it gets you all the data and sorts it out neatly. So what you want to know is, can we get rid of some data? What you will see here is that, some quarters have more observations. So it's the half-year data and the end-of-year data have more observations than the September and June data, or the September data and the March data. So something to bear in mind. Probably you get only the key variables every quarter, but additional variables not. Now, to get an idea about the data, you can sort of, use, if you want to know what these mnemonics mean, then I wrote this in such a way that you can put it into a dictionary, and you can sort of easily use that dictionary to look up various values. To look up what, for example, does it mean BHCK 2170? Well, that's total assets. So I wrote a dictionary where you can look up the labels of these mnemonics. For data date, last week there was somebody asking me whether you should whether the date column, which is RSSD, and just let me check. So what you can see, there is a column called RSD with 4 times 9. That is a date column. So that's your data date equivalent for the period. So it's 2019-31. So that is end of March 2019 data. And then this one here is 31 of December 2021. So that column can be used as a date column, which for which apply this command here, df data date, and then it turns your RSS 4 times 9 variable into a date. Now, stuff we may not need. Oh yeah, we only want to keep data with values, valid values for equity and for total assets. So we're going to drop all the variables if they have report missing observations for these 2 variables. So that's done with the drop now command. And the resulting data frame is not 24,000, but only 4,000, about 4,000. So you reduce a lot of value by just eliminating observations or rows with no equity and no total assets. Yeah, so these are useless observations for our work. And so we drop them using drop now. One thing you notice if you do value counts, you will see that for this year or for the end of 2021, there's only 2 banks participating in the sample. So we eliminate that using the location command. And select only from the data date, select only values from your data frame where data frame is unequal to the 31st of December 2021. And then you can see if you do, if you look at the value counts of the data frame or data date, you can see that it's a fairly constant sample now, which is more easy for you to do research. Now, once we have a date variable, a date column, and an identifier column, we can use that to create an index, which is done using the setIndex command. Sometimes I use in place, whenever I'm just lazy. If I do in place, then I don't have to, the alternative approach would be to do it like this. Say the data frame df is df setx index. That's equivalent to in place is true. I tend to use in place is true because it, easier to, it's shorter to work with. If you check that everything works here, you can see we have now a nice data frame with an identifier, which is a bank identifier, a date, and then we have, variable names here. This is the state name, and here you have your other variables. So we now have a properly formatted data frame. Again, here, identifier and date to the left, variable names as columns. That makes it easy to find a bank. So if I want to find the Citibank, the identifier is here 1951350. If I locate that using the index, basically I'm appealing to the far left column here to get the observation from city. And you can see here this small data frame city is 2 rows and 22 columns. Okay, I can do the whole column here. Okay, forget that. Now, if I do the whole thing, then I'll probably get the whole check. I can do it with Bank of America and Citi. Wait, this should work. Oh yeah, this is the whole Citi data frame. Oh yeah, so there's only 5 rows available. No, not true. This is it. This is Citi, starting from 2019, ending to September 21, and this is your Citibank data frame. So total assets about 2 trillion, equity about 10% of that. We can also look for Citi and Bank of America combined, so we can combine these numbers, or Citi is the identifier for Bank of America, and then we do it like that. And then you have your combined Citi and BOA data. So it starts with Bank of America here, that's the head of the data frame, and the tail is Citi. A couple of things you can do is replace. Sometimes you see values of 0. So in some cases, there is a 0 value for the state. I'm not sure if we've seen that before. Here, for example, it says state is 0. That should be a missing observation. So we can use this replace command, turn all these zeros, text zeros, into a missing observation. And then you have properly identified the missing observations for the state, abbreviated state name. If you want to apply the same trick for risk-weighted assets, you should not put quotes around the 0, because the 0 in the state name is a text, is a string, whereas the 0 in risk-weighted assets is a number. And so you should replace the number 0 by nans for risk-weighted assets, because there's no bank without risk-weighted assets. Yeah, if you do that, you can see you only leave with the minimum value for risk-weighted assets then becomes something like $28 million. Okay, now we have a properly formatted data frame, and we can sort of do some, play some tricks with it or do some analysis with that. One thing is to measure the development of bank liquidity. So how liquid have, how much cash do banks have? Yeah, so we're looking at the left-hand side of the balance sheet, cash, not like capital, which is on the right-hand side of the balance sheet. So cash can be defined by looking into these items, which are, you can go to the dictionary above, this one here, and you will find that I designated a couple of variables from this list here that can be seen as cash or near cash or deemed to be cash variables. Yeah. So this is cash. That's the sum of these variables here. 4 variables that define cash. And if I sum that, normally the data frame will take the sum at the bottom, like, at the bottom of your data frame, and sums up all the columns at, like an additional row at the bottom, or sort of, that's how normally the sum command works. So it creates, it basically shows you the sums of all these values. But what you want is to create another variable called cash, which is the row sum of these variables. So you have to tell Pandas that you have to sum the columns, not the rows. The default is rows, so you have to tell it the axis should be focused on columns, and then you get the sum of the columns, which then creates another variable called cash in this case. With that cash variable, we can divide it by total assets, just, that's 2170, and then we create a liquidity ratio. It's not the liquidity coverage ratio, as we know it in banking, but it's just a liquidity ratio, which is the ratio of cash over total assets. And then we can see if that is well behaved by applying the histogram command, sorry. And then we see that, the liquidity ratio is well behaved, there's no outliers, and the maximum is below 1, which would make sense because there's no cash, no bank that has more cash than total assets. So it should be less than 1. Now, again, using group by, we can look at the liquidity ratio over time, and then we see an increase in the liquidity. Yeah. So that's the main part of the assignment. So we can apply the same stuff to capital ratios, and then we can group and show the evolution of capital ratios for US banks. And then we can do some other stuff, but in the interest of time, I'll skip that. The main part was this, and the focus should be on manipulating your data so that you have a properly working data frame, which we now have. Question to the audience: why did liquidity increase so much over time? What you can see. So I'll leave that to you to answer. Any good suggestions? So one was the reason, obviously, was COVID. The Fed started injecting a lot of cash into the banks, and that should, that is clearly visible here in this line here. Yeah. So I'll leave it at that for now because it's exactly 11 o'clock, and I'll open up the floor for some people that have questions. Yeah. if it's all right, this file here with the solutions is available, should be available on the on my Netlify, the main website and the GitHub side of this. So then, you can run this. And according to Ricardo, you ran this stuff and it all worked. Yeah, that's what I do. I make sure that it works before I post it online, which is, add some work to my workload, but fair enough. If you cannot have these jobs not working. Okay, any questions? So far, so good. Okay, then I'll leave it at that. I'll hang around, and the assignment or the stuff for Thursday has been posted already on the on GitHub as well as the Netlify account. I think. What is that? That's this one here. So if you go there. So session 7 is the slides are available for you, and I'll hope to see you on Thursday.
Martin, can you tell us something about the next session?
Yeah, so the next session is actually going to be interesting in that we're going to work with price data. So we're going to make a proper accounting research data set using prices and returns and cumulative returns, and then associate them with accounting data. And this time, again, I will be using bank data, but it's the same accounting data as from other sources. So, and that sets us up for, regression analysis in the last or penultimate or last session. So by the Thursday, we have all the tools that we need to merge prices, price data, share price data with accounting data, and perform, some analysis on that stuff. Yeah. So again, I invite you to if you want to understand it better, just go ahead and run this on your own Jupyter notebook, and then you will notice that everything works. And so, by that time, if you completed that until session 7, you're pretty much up to shape to deal with all this this data.
So, Martin, in case they did not attend the last session, what do you suggest for them? We have everything available, right?
Yeah, everything is available online. So, though, there's part of that can be, most of the stuff is self-supporting. So even if you're just late in the day, if you catch up with session 7, the notebook is set up in such a way that you don't need to refer too much to previous sessions.
Okay, thank you very much for everybody for your participation. Thanks for Martin.
Thank you very much.
Thanks, Martin, for this new session. And I would like to invite everybody to register for the next session, and also tell your friends to do the same. Thank you very much.
Thank you.